Okay, so our next presentation is by Charles Lattimer, and Charles is the project director for Atkins North American Federal Business Unit, and with expertise in ITS and traffic operations. He is the vice chair of the TRB Standing Committee on Visualization in Transportation. He also chaired the subcommittee on performance visualization under the big ABJ 85. So Charles is going to talk to us about using automated traffic signal performance measures visualizations to improve traffic signal operations. With that, Charles? Thank you.
Thank you, Pat. Is there somebody back there to change the presentation, or? Oh, there we go. Oh, okay. So.
Where did you put it? It's just on the desktop?
I think there's a folder that they're all in, or it may be up at the bottom of the screen too. I'm not sure, but it may be, that's the one right there.
Right there?
Yeah. There we go. That's it. All right. Well, good morning. I'm Charles Lattimer, and I'm happy to be here today. So we're going to talk about something a little bit different. ATSPM. So we're going to be talking about automated traffic signal performance measures. I title this Visualization in Action because as I've been learning more about ATSPM, I've been very excited about how ATSPM can be a decision-making tool to allow traffic engineers to better improve their signal operations. So let's. So most of you, I'm sure, are aware of the problem of traffic congestion if you've ever driven on the roads recently. It's kind of a complicated situation. We have, obviously, traffic demand is increasing. The number of cars, capacity, can't always keep pace with the number of vehicles that are driving on the roads. And at the same time, the funding for operations, we're seeing some downward pressure or limitations on funding, to improve those operations. And so, wouldn't it be nice if there was a tool or some way that, traffic engineers could look across their entire state and see, what the conditions of the traffic signals were and how they were operating? Well, good news is there's something, it's called automated traffic signal performance measures. This involves the visualization of high-resolution traffic data from the traffic signal controllers to improve operations. It was a collaboration between FHWA, AASHTO, state DOTs, and various academic institutions. I believe Purdue was kind of where things got started with that. There was a transportation pooled fund study a few years ago that funded the development of open source software for use by other states and agencies. And so we're going to see some examples from that open source software. Right now it's Utah DOT is kind of the keeper of that and maintaining that, but other states, like Florida, Georgia, are collaborating and adding new content into that software, which are then included in the future updates. So the benefits of ATSPM we see are targeted maintenance, improved operations, and increased safety. Where I kind of came into the picture is that we were, as my company, we were able to help out FHWA promote ATSPM under the previous round of Everyday Counts 4. For those of you who are not familiar with Everyday Counts, it's organized by the FHWA Center for Accelerating Innovation. And what it does is they select every 2 years a handful of proven but often underutilized innovations that really help accelerate and improve the delivery of transportation projects and operations. And the idea is just to get the word out there and have workshops and case studies and webinars and peer exchanges, and make sure really make sure other state DOTs are aware of that technology and can rely on that. And so we went across the country to promote some various workshops, and it's just, we were seeing that, I was really impressed, like I mentioned before, was how agencies were really using this to transform the way they do traffic signal operations. The old method is you go through the process and, there's a triggering event, there's a complaint, it's every 5 years and it's time to retime our traffic signals. You do the project, you collect the data, retime it, and then you're done with it. And then, what this allows you to do is to, if you can really build that operations culture, to be able to go through and, be able to really update and check the performance of your system in real time, and changes that would have taken like a project to do, you can really just make those in like 30 minutes by looking at the data. So let's talk a little bit about how it works here. So traffic signal controller, which is out in your cabinet, so that really works, it's a computer, works on inputs and outputs, goes ins and goes outs. So your inputs, you might have your detectors, your activation of your detector when a vehicle rolls over something, somebody pushes your pedestrian button, and things like that. And then outputs out from the detector. You've got your, maybe the controller tells the phase to turn green or to begin, or okay, this phase maxes out, so how do we, okay, you've had enough time, we're cutting you off. So, or let's activate the pedestrian walk beacon. And so this information, each one of these little inputs and outputs is sent to a high resolution data logger. And at every 1/10 of a second, it's written to basically a text file. And what that data file does, you can see there's a timestamp, there's an event code, and an event parameter. And so the event code, those are called enumerations. So every one of those individual inputs and outputs has a number, and that's coded. And then the event parameter is like where, on what approach, what phase did that happen to? And we'll talk about phases in a second. But what ATSPM then does is takes that table and turns it into human readable reports and graphs. So these are some of the basic system components. You have to have a traffic signal controller that is capable of high resolution data logging. Most of the new ones you buy off the shelf today are, and so that's a good thing. You have to have communications somehow to get that information, that log, that text information back to a central server that's running the ATSPM software. And we put detection as optional here. You can run ATSPM without detection, but it's just a very, very limited set of reports. So there's a lot more you can do with it if you have detection in your lanes. So this is what the user interface looks like. This is Utah DOT. This is a screenshot off of their system. And so what you do is you can see on the left-hand side, we've got a map that you can zoom into and zoom in and out of and pick your signal. So the first thing you want to do is you select your signal and just click on that. And then when you click on that, the available charts will come up, and that depends upon what kind of detection is configured and what other things are set up at the intersection there. And so in this case, we're going to pick the Purdue phase termination diagram. And then if you want to customize that at all, as far as with your y-axis or any kinds of options there, you can pick that over to the right. Choose your date range, and then click Create Chart, and that's really all there is to it. And so what would happen if you do that, then right underneath, you just kind of scroll down and your chart would just appear there as a JPEG image. So we're going to take a look at two visualizations as part of this. We could spend basically all day, full day workshop going through all the different kinds of charts and visualizations that can come out of ATSPM, but just want to focus on two today. In fact, I believe a next presentation is going to kind of go a step further, what happens, kind of a next generation of ATSPM when you start throwing probe data into the mix here too, so that's going to be, I'm looking forward to seeing that. But, so one couple definitions here before we go into the first chart. So when we talk about a signal phase, so that's going to be kind of what you see up here on the, oops, let me go back here, can I do that? Anyway, all right, there we go, perfect. Okay, so there are basically 8 signal phases that you would see at on a traffic signal there. So there's the pretty much one of the 8, and that represents one of the 8 major movements that you would see at a typical intersection. Usually like the through movement and the right is kind of grouped together into one phase. And you can see like on the graph, on the little chart here, the ring diagram here on the left, some of those phases can run at the same time. Like your opposing left turns can run at the same time, your opposing through traffic can go at the same time. But basically your cycle is running through those entire phases, you know, kind of making sure all the movements are served. So this is what the Purdue phase termination diagram looks like. And you can see here on the, so you've going up on the, there we go. On this side, these are your phases, so 1 through 8. And a traffic signal engineer, there's a convention to this, so they would understand, you know, what movements correspond to each one of these numbers here. But you know, for our cases, this is the through movement here on the major road, number 2 and 6. And what this does is this talks about how did my phase end, you know. So when you get to the, you know, you only have a certain amount of time allocated for your phase before you have to go on to the next one. Sometimes it might gap out, and that's kind of what's shown in the green here. So you've probably been sitting at an intersection, you've got traffic coming through, and there's a big gap in traffic, and then it turns red, and then it's your turn. Then it's your turn. And so gaps out. If the traffic stops flowing, it'll stop it early, and then pass the time on to the next phase there. Or kind of the other end of the spectrum is the max out. So I'm going to take as much time as I possibly can, you know, and you're going to have to cut me off here because you got no more time. We're moving on to the next one. So this is an example that came from UDOT. This is kind of one of their very famous examples. If you've seen some of their presentations, you probably would have seen this one before. But so you can have a citizen calls in, says, you know, I come home from work at 2 o'clock in the morning. I'm going home on my major road. There's no traffic on the road, but I keep pulling up to this stoplight, and I'm sitting here. There's no cross-track. I've got a red light. You know, what's going on? You guys obviously don't know what you're doing. So then, under the old way, they would get that call in the morning, and then the traffic signal engineer or the technician would go out to the field at 2 o'clock in the afternoon and say, my detection looks fine. Everything looks normal. I don't see what the problem is. Things are working good. This person must be crazy. So with ATSPM, what you can do under the new way is they can pull this report up, and they can say, well, let's take a look at this here. This is running free, so it should just be responding just to the traffic that's there. But we're getting a lot of max outs here on this minor phase. So you got a cross street with no traffic, but it's taken up its full time, so something's not going on right there. But then you also take a look here, and right about 9 o'clock in the morning, things seems to fix themselves. And they work good during the day and work good here, and then at night things get dark, they stop working. So it turns out in this particular situation, there was a problem with the video detection not working. And so you have TV cameras, video detectors looking for traffic, and it's dark. I think the street lights are out or something in this case. And so it wasn't able to see the cars properly. And so it gave a false call to these movements. So knowing that, then the technician was able to go out during the day and make that change. And then afterwards, about a week later, you can see it fixed the problem. So the other nice thing about this is, you know, the technician can make the change during the day and then pull the report from the next day and not have to go out at 2 o'clock in the morning to make sure things are working. So that saves a lot of time on the maintenance staff too. So this would have been a very hard problem to catch without something like ATSPM to really visualize this. Our second example is the Purdue coordination diagram. This is kind of one of their really famous visualizations that come out of this. If you haven't seen this before, it looks like a mess when you first look at it. But if you really take a look, this is a very elegant visualization. There's a lot of information in here. You can see there's a black line here that shows the volume coming from the intersection of the particular movement. And this is a single phase of traffic. So this might be looks like the northbound through movement, you know, for the traffic here. So these green lines show this is when the signal turned green. This is when it turned red. And each one of these little dots here represents like one car going across a detector. And these are usually like upstream of the intersection. And you can see these bands here, these shaded areas. So this shows your signal timing plan. So this is free. You've basically got 4 different plans here, you know, that are coordinated depending upon time of the day. It looks like free running out here. So jumping into this a little more, let's kind of slice and dice this a little bit. So So if we just take a look at one of those signal plans, so the way this works here is we have time of day going across the bottom axis and the cycle time going up. And so you're basically, if you really zoom in on this, you'd see like a kind of a slanted line of dots here kind of going up. And so what happens is your cycle begins down here at 0, and then this is red time, so then your signal turns green, and your signal turns red up here, and then for the very next one it drops back down here, and you just kind of keeps going up like that. So, and your cycle ends. So below the green, if your cars arrive before it turns green, they're arriving on red, and if they arrive in this zone, they're arriving on green. This is bad, and this is good when you're trying to coordinate traffic signal timing. So what can that tell us if we look at this diagram here? So up here you can see the percent arrival on green. So this is a nice little metric here that tells us, so this is 47% of my cars arrived on green over this time frame. This is pretty good. We have most of our dots here up in this area. If you look at this plan, you can see there's a group of dots down here at the bottom, and what this might suggest is we've got cars arriving that are, just after the signal turned red. So maybe we can give a little more, either more time to this signal, or change the offsets, to kind of, have these cars, arrive up in this area. So here's another example from UDOT. So this is, if you like before optimization, you might see something that looks like this. A lot of cars clustered here on the red, and then afterwards, they're bunched up here in the green. What you can do is you can then stack these. You can make several of these and put these in and take a look at corridors. So, for instance, in this case, we have southbound traffic. This might be our first traffic light. So these are random arrivals. So people are just coming off. There's no traffic light, and they're just coming in at random times. Then as they hit the traffic lights, they start grouping together into platoons. And you can see here that this one's okay. It's kind of distributed. This one's good. Most people arrive on green. Oh, got a lot of red ones down here. Kind of vice versa. Kind of going out of town. So after optimization, then you make your changes. You can say, oh, okay, things are getting better here. So we're getting more cars up in this area, and occasionally, sometimes the fix is not perfect. So some of these might get a little bit worse, but overall, the idea is to get, if you're going for a progression, the idea is to get these up here into the green zone. So I'm going to kind of flip these back. We'll kind of do our little eye test here. So that's kind of before and after. All right, so I'm going to end with a few resources here, and obviously feel free to take a picture here if you'd like to of the screen here. I think some of this will be published as well here. But we've got, so these are three states here that have public ATSPM websites that you can take a look at. You can just log in, pull up all these same charts and check them out. So we have at the top here, UDOT. And if you pull up this page here, look at the top here, there's presentations and frequently asked questions. So there's a lot of information and presentations here on diving down on how these metrics are calculated, what they mean, and how to use them. So we have Florida as well. So Central Florida, the Orlando area, they're loading a lot of signals in there for Seminole County and Brevard County. And Georgia also has ATSPM that they're using statewide. FHWA has a page here under their arterial performance measures program area where you can also get publications, webinars, and the case studies, and also the example system. So I encourage you to check that out, if you're interested in learning more. All right, so we have time for a few questions, if anybody has any questions. Is that someone in the back or no? You're just, no, okay, all right.
Could you expand on the automated part? Are any controllers capable of interpreting this type of data and calling you when there's problems?
So yes, there's another section, so a little distinction there too. This rides on top of the controller process kind of in parallel. So these don't actually control the signals in the sense of like an adaptive system, but there is something called a watchdog process. And so what it'll do is it will run in the background, and it will look for things like, kind of like we showed up there, like if, are there some, like at 2 o'clock, over a certain period of time at night, are we seeing signals maxing out? Are we seeing odd conditions? And it'll run that overnight, and then it'll send out an email at 7 o'clock in the morning for technicians. So that's one thing that people who have really embraced this have, they've seen their complaint calls go down because they're able to get a call, an email first thing in the morning, and a lot of times they're able to catch an issue before, Joe Public comes in and calls and reports it. So very good question. Thank you. Yes.
So how difficult is it to modify? So yesterday we heard there's some kind of suggestion or proposal to time the pedestrian signal,
Okay.
depending on the pedestrian, if it's a wheelchair, if it's elderly.
Mm-hmm.
So the timing for the pedestrian might be different. So how responsive would this system be in incorporating that kind of flexible?
So that's a good question. So the way ATSPM incorporates it is there is something called a pedestrian delay, that metric that's in there, but that assumes that it's going to be the same ped time. They would probably have to there probably have to be a new enumeration that would have to be created to. Because it sounds like then, like you'd have different kinds of PED calls then. It wouldn't be so they'd have to pretty much expand that enumerations to be able to differentiate between what those PED calls were. But by doing that, you could then probably have a good mix of what's my population look like of pedestrians. So that's a very interesting idea. Yeah.
Anything else, Charles? Thank you, Charles.
Thank you.